I get the post-lunch coma crowd. It wasn't that heavy a lunch. You shouldn't be all that tired. How many people saw the presentation yesterday really quickly? Raise your hands. Great. You're going to be bored out of your minds. No, I kid. So I would like to start the session off really quickly. We only have a 20-minute session, and as a result, I want to make sure that you get your money's worth. So my name is Jay Metz. I am a technical director for advanced storage and networking for AMD, and I'm also the chair of the steering committee for Ultra Ethernet Consortium. And my co-presenter, or your co-author of the presentation, Uri, is the technical advisory council or committee chair. And he did a presentation yesterday, went into some technical deep dives about this. So I'm going to go ahead and try and make sure that I can kind of fill in some of the gaps from these two conversations that we've already had. And I do want to encourage you to be able to ask questions. We've got a couple of microphones set up for you. Please do feel free to come up and ask questions. I will answer as many as I possibly can given the time that we've got. So the question about Ultra Ethernet Consortium is really kind of an interesting one. We are a relatively new organization. We only really announced the existence of the organization a year ago, a little over a year ago. And in that time, we have gone from an original 6-member companies to over 100 in a year. So it's an incredibly fast-growing organization, and we have developed an environment where people who want to have an open ecosystem for high-performance networking at scale can be able to join and contribute to the specifications. Now, what are we trying to do? Well, we have an incredibly ambitious project that we're looking to accomplish, and that is we want to take a standards-based approach to solving problems in the network that we find when we're doing AI and HPC workloads. Now, AI and HPC workloads have some things in common, but they don't have everything in common. They're not exactly the same. Some of the workloads are latency bound. They have very highly sensitive to latency, and some of them are bandwidth bound. Some of them are memory bound. And so when you start to look at the way that the network responds, given what happens inside of a workload, you start to realize that you can't just simply tweak a particular layer inside of Ethernet or any kind of network for that matter and expect to have magic happen. As a matter of fact, when we get into these really large systems, we're talking, we count in terms of the number of CPUs, the number of GPUs, but we talk in terms of endpoints. What constitutes an endpoint is more than a GPU, it's more than a CPU, it's more than a NIC. It is now an endpoint could be an endpoint on a GPU, an endpoint could be on a CPU, and so on and so forth. So what we're looking to do is say, hey, I want to tune that network for the workloads. And we need to make sure that the intelligence is working really well for the network to be able to do that. So we've created an ambitious project, an incredibly ambitious project, to be able to handle all of the network layers that you're used to inside of Ethernet, and also combine them for checks and balances through those layers to make sure that they're all aligned for those workloads. For instance, if you were going to take the physical layer and you want to make it work with the link layer, you have different types of requirements that you need for AI types of workloads as you do for HPC and so on and so forth. Link layer has to be able to merge with the transport layer. The transport layer has to be able to work well with the software layers above it. But they're not all the same, so you wind up with somewhat of a pachinko chip kind of a thing, trying to get to the appropriate connections through these different layers. So we decided that we're going to take this cross-hatched approach where we have checks and balances and accountability both inside of the spec, inside of the standard, as well inside of the organization itself. So we have our standard approach to solving these problems while making tuning requirements and changes inside of the group. And it just so happens that we have a lot of different organizations and companies that wish to do this as well. At first, it was just a small group, and to be honest, didn't really expect that it was going to take off the way that it did. When we first started thinking about doing this, we thought maybe 15, 20 companies were going to be interested. We had no idea that it was going to take off. It turned out it was the largest or the fastest growing Linux Foundation project in history. So we have over 100 companies that have already signed the paperwork and are joining and contributing. We have another about 40 or 50 that are completing the paperwork to join. So it is an incredibly ambitious project that has captured the hearts and the imagination of a number of different companies from around the world. And it's absolutely fantastic. So let's talk a little bit about what it is that we're trying to accomplish here. Now, for those of you who may not necessarily be gurus in the AI load or the data center load, really quickly, how many people are networking people, or you consider yourselves to be networking people? Okay, how many people are compute people? How many people just like raising your hands? Nobody. Oh, okay. A couple smart asses. That's a good sign. Okay, so when we start to work on these different types of workloads, we have different types of networks that we attach into these different systems to be able to accomplish different things. Generally speaking, in an enterprise, you have a general purpose Ethernet network. That's what makes Ethernet so wonderful and so fantastic. You can use it for anything. You can do multi-tenancy, you can do multi-pathing, you can do all kinds of types of traffic. You can do storage traffic, you can do east-west traffic, north-south traffic. It's perfectly suited for that kind of general purpose traffic. When we want to do specific types of workloads, we create a separate network. We create a back-end network for this. And Ethernet is also suitable for that as well, because of the fact that you want to be able to create this workload, and this is the back-end network that we're looking to do for scale out across all these different systems, to be able to interconnect these different devices with a dedicated network that's specifically tuned for that workload. Instead of a general purpose network, we're looking for a more workload-specific one. And then we have a third one, which is actually the way that we want to create one giant, large network for the accelerators. In this particular case, we talk mostly about GPUs. So if we wanted to create one honkin' memory space, we're going to do is scale up. If we want to connect those big, huge honkin' GPU memory spaces, we're going to use UEC. And so that's the idea of having three different basic characteristics for the different networks, because you treat them differently, you implement them differently, you characterize them differently. So one is load store for the scale up, and then we have DMA for the scale out. And then you can have any other kind of packetized I/O for the general purpose. And you use the one that you need when you need it in order to be the most efficient and make sure you have the least amount of idle time. So, I see that my co-presenter is here now. You want to come up and share the stage with me?
Okay.
All right, so this is Uri. Uri is the Technical Advisory Committee Chair, and together we've been we're working very closely on making sure that this is becoming a reality, and we're very close to technical stability as far as. You want to go ahead and take over on this?
Yeah, so just in the interest of time, noticed a few folks here are network folks. The challenge we took on originally was not only to address AI, but also HPC as well. And what this slide is trying to capture in a nutshell is the kind of the different ways these different types of application kind of perceive what they are looking the network to deliver for them. So on the left side, you see, and this is mainly true for training, because inference has its own pressure, like with latency sensitivity. But what this is showing you is that training is bandwidth sensitive, and that the goal there is really to make sure that the communication time doesn't really creep up on the whole, call it job completion. So you want the network, the ideal situation is that you could hide the network behind all of your compute. However, AI is systolic. You cannot always do this, and we have different, between EP, TP, PP, and DP, all of the different flavors. Sometimes you could hide it, sometimes not. But the message here is, hey, it's bandwidth sensitive, and we want to do the best we can for the network utilization as well as the tail latency to make it as small as possible. In comparison with the HPC guys, where normally their messages are really short, they are very sensitive to drops. AI has very large messages. As an example, Ultra Ethernet is recommending you run at 4K byte MTU. That works very nice for those training situations. So the key questions that are coming out of this slide is like, okay, you have two potentially diverse use cases. Can you really come up with one technology that is happy for both of those somewhat different ways of measuring what the network can do for you, as well as different requirements? And the next slide is going to answer that question.
Yeah, but before we get there, I just want to back up a little bit because the AI workload itself, and you kind of went through it really fast.
It's a short talk.
I know it's a short talk. Out of curiosity, how many people are familiar with what he said when he said EP, DP, CP, and those kinds of things? Okay, so let me just take a quick level set here, real quick. When we do AI workloads, you've heard of training and you've heard of inference, and a lot of people stop there, okay? But training workloads and inference workloads have very different needs. Some are very latency bound. Inference is they use smaller packets, and some are training methods. They have large packets and large amounts of data that goes back and forth across the different networks. However, when you start to talk about these models, these really large models like the 405B, the 1 trillion parameter, the 10 trillion parameter that they're talking about in the keynotes, the trouble is that the amount of memory you need to be able to handle that is enormous, right? So your GPUs need to be able to address anywhere up to 32 terabytes of DRAM. No GPU on the planet right now can go anywhere close to that. So you have to be able to create these GPU memory spaces, and the way that you accommodate that is through what's called parallelism. So you can do data parallelism, you can do pipeline parallelism, and we're not going to go into those details now, but that parallelism is a way of breaking up the workloads and being able to communicate the data between the different memory regions and use it at the appropriate time during the cycle of the passes that go through in the AI training. You with me so far? All right, this is the audience participation portion of the day. Okay, thank you. Thank you very much. All right, and what Uri is talking about is that each of those types of parallelism has different networking requirements. And what we're looking to do is handle those networking requirements for each of those different parallelism types. Right? And that is the idea behind going forward with the AI types of workloads versus the HPC types of workloads. And because of the fact that we use different types of processors to do it, the way that we interconnect into the networking stack has to be slightly different as well. That's the purpose and the reason why UEC is doing what it's doing. Now,
And to add one more sentence to what Jay just said.
And one more thing.
One more thing. What we are witnessing also is that the HPC applications morph and migrate themselves. And in some cases, you find customers who used to be pure HPC, but now they also rely on some AI part of their application. So that gives you another motivation to come up with a technology that addresses everything. And for all of those parallelization stuff, yeah, we need a little bit more time to cover that. But thanks, Jay. So
watch this space. We'll be getting to that when we get to.
What we are trying to communicate on this slide is here are the basic tenets that you need in order to build a successful networking solution that, as Jay started this talk, is about to take Ethernet from where it is today to that era of AI and HPC. And yesterday, we delivered a more technical talk. So if you want to go, and I don't know how much time we have, so I don't know that.
Right now, we've got 7 minutes.
7 minutes, okay. So on the left side, on the upper left side, you see a typical description of a protocol stack, and that dashed line shows the areas where Ultra Ethernet is focusing, everything within the box. The key takeaway messages from that are the following. You see that the applications, be it AI or HPC, are outside of the box. Takeaway, we are not asking any change in the workload. You could take the existing workload, it is going to work seamlessly. What we do for that, we actually provide APIs that are relying on libfabric. libfabric 2.0 has some extensions that the Ultra Ethernet community is driving into it if you want to benefit from some of the good things that we are doing at the transport layer. The other thing at the bottom is actually a standard Ethernet. Actually, it's not only Ethernet, it's an IP packet. So we are really working on IP packets. You have an existing infrastructure, and that was a request from our hyperscaler customers. Existing data center switches work with Ultra Ethernet. Yep. Where is all the smarts? Where is all the innovation? Well, that happens on the endpoint. So you only need to change the endpoint in order to get there. And what you need to do on the transport, which happens to have the key innovation, while we have optional features that are going to even make your ride even more interesting, both on the switches and on the endpoint. Time is too short for that. But basically, that list are areas where you want to go and change and update and modify what the industry has done in the last 20, 25 years. A key takeaway message, separate the RDMA capability from the transport that carries it. RDMA is good news. It's kernel bypass, no software, no CPU needs to be involved. It all runs at the hardware speed. The transport that comes with it, well, we want to do large scale. We want to do multipathing because AI, and Jay started by saying how different are these networks and how different are the requirements, but AI is a systolic thing. It actually is one time compute, another time is doing communication. It's very symmetric, and I could build on this. It makes my congestion simpler. Another quick example is HPC originally, if folks here are aware with the requirements that are coming from MPI, was rigid point to point. You need to keep state, a Q pair on both ends. It only runs on a single path. When it gets into trouble, you have go back N, you need to retransmit many. This list is all about the areas that we are doing things better to allow you to get, if you could click the next one over there, to get, and the last one as well, is actually to get to the best job completion time. And that is, you achieve that by addressing the big challenge of high utilization plus keeping your tail latency, which really means, if you want to think about it this way, you have thousands of flows up in the air or on the wire, and you want to make sure that they all reach there at the same time. It gets much harder when the scale is larger. And this is a key difference between how those specialized network, as Jay pointed out, are running as compared with the standard data center network.
Yeah, and where we realized very quickly was that small degrees of changes in error inside of each layer has amplification effects as it goes up the stack and down the stack. So for example, the faster you go at the physical layer, the more those errors start to compound and start to create inefficiencies inside of the network, even at the PHY layer, right? So the work that we're trying to do is to create a bond between the link layer and the physical layer by using the standard Ethernet physical layer, that is, to be able to have that communication better and stronger. And we do that all the way up the stack so that those synchronizations are consistent. And as you can imagine, that consistency is very important when you get to really large scales, millions of endpoints. So we want to make sure that we have that all set up. And what you're seeing here is a really high level. It may not look as if it's new to you, but it's a high level of being able to identify at each layer where those touch points are that are going to be synchronized across up and down the stack.
Yeah, so this is a loaded slide. We can present this slide by itself for half an hour. Let me try and walk you through this as quickly as possible. So you see here the whole communication stack. Mind you, that little legend at the bottom that shows you what we preserve as it stands and what is required. And if you look carefully at what is required, it's really those extensions at the lib fabric, which is a library. Again, doesn't change the workload. It's a library that we are creating as a reference. Then you have the transport, where lots of innovation happens. And then at the bottom, you actually, this is recommended. You could run slower, but we recommend the 100 gig because actually all modern accelerated servers are starting at that point. The industry is at the point of trying to transition to 200 gig signaling. You notice also that we have many optional features. And I think probably the most interesting, again, in interest of time, because yesterday we had much more time, we got into much more details. So I'll just touch on few points. There are two transport services that we are doing: the reliable ordered delivery and the reliable and the unordered delivery. So the ordered one helps you to preserve the ecosystem that you had should you have an HPC workload, or if your AI workload at some portions of the time does really need ordering for whatever reason. Most of the time, the ordering would be required in order to point you to a specific buffer. Some applications do this. Some of the key innovations that we have done is on the unordered. Just to give you a feel for this, imagine that you are sending, you have up to 1 million endpoints. Each of them is trying to share 1 megabyte, 1 gigabyte. Many packets are flowing, each of them on a different path. So you cannot preserve the packet level ordering. That makes the utilization of the network much higher, but then it comes with its own set of problems, because a packet that packet n and n+1 and n+2 part of the message, they don't necessarily arrive at the order they were sent, because each of them is traveling on a different path. How do you deal with that? So there's lots of interesting, good stuff that we have done in order to deal with those problems, while we are not asking for additional space, power, die size in order to keep state. Our state is much more flexible. So you take the software APIs, the hardware, and the network, and you simply adjust them to what AI is asking of you.
Yeah, and so in the interest of time, we're already over by a couple minutes, so we're going to have to close. But we do have on ultraethernet.org, we've got white papers, we've got blogs, we have additional information, including some of the pretty pictures that you see here. We will be doing some more videos when we get closer to the 1.0 release, which we're expecting to be published in the first quarter of next year, where we're going to be doing videos of some of the different things that Uri was talking about in greater detail, and we'll be able to provide those things for you. So I do highly recommend that if you're interested in more information, that you do check out the website for those blogs and those news articles. So I do think that you're going to see a lot more information coming out from the members of UEC with their products coming out. We've already had a couple of announcements very recently, especially in the software level. That's going to be coming out as well. So out of respect of our colleagues who are waiting patiently, I'm going to go ahead and pass this off to making sure that you all know that we're doing some really good stuff with OCP, including some of the switch stuff, including some of the congestion signaling as well. So any last thoughts?
I think, yep, time is up.
Well, thank you very much for your time. I appreciate it. And see, we still have some standing room only in the back. Yeah, you're more than welcome to come and find a seat while we do the transition. Thank you, everybody.
Thank you.